All right. Okay, so to start us off, all right, so the word model. What we're talking about here is that we just have this physical representation, something that is tangible to us so that we can focus in on these things that we can't see. So we have the atomic model. That's what we're saying. And all those guys called their little model a different thing because they're trying to define what this really tiny particle that nobody can see is. Okay? So that's what we do want you to focus on. Okay? All right. Democritus was the first guy, 400 BC, right? And he's the one who first came up with that word atom. Okay? He took it from the Greek word atomos, meaning indivisible. Do you guys know what indivisible means?
No.
Does anybody? No. Raise your hand if you got it. No? Okay, so what does divisible mean?
It can be divided.
It can be divided, right? Indivisible is in our Pledge of Allegiance, by the way. So indivisible means, so if divisible is divided, what is indivisible? Together, can't be divided, okay? So what he was saying is that the atom is the most simplest thing there is in life. So it doesn't get any smaller than an atom. That's what he's saying. So you guys have a little light bulb on your page. Go ahead and write down what does indivisible mean. So can't be separated. Okay? All right. So that's Democritus. This is what he did. So he said it's a dot. All right? So all our atoms are a dot. There's nothing smaller. There's nothing inside the dot. It's just a dot. And that's what makes up the whole world. Okay? But then Aristotle, he didn't agree with him. He was like, no. You're wrong. There's 4 elements. There's earth, air, fire, and water. Because if you look up at the sky, air looks a certain way. If you look down at the water, it looks a certain way. When you look at fire, it's a different way. So there's only 4 elements in the world, and that's what makes up the whole thing. Okay? Everyone went with Aristotle. So we believe that for 2,000 years. Okay? And who ended up being closer to being right? Democritus, right? So, Dalton, okay? Please notice that year. We started at 400 BC. Now where are we at? 1808, right? Long time later. So Dalton finally went to this whole idea and he made it official, all right? So he kind of took Democritus's original idea there and he went with, there's little atoms, okay? But these atoms can't be divided. So he just kind of, what I like to think of is Dalton was kind of like the Bill Nye of the 1800s. So, because all of you guys memorize everything Bill Nye tells you, right? Yeah. Like Bill Nye is really good at communicating really hard stuff, in my opinion. Okay? Dalton was really good at communicating really hard stuff to the general public. So everybody jumped on board. Okay? So he said that can't be divided. His theory included 4 postulates. He had the conservation of mass. He had definite proportions, multiple proportions. Okay, definite and multiple proportions is in that box on your page. We are going to get to that tomorrow. So we're going to skip that box. We're going to focus in on the 4 postulates. They're at the bottom of the page. So look at those with me down on your page. There we go. So that moves us to, okay. All right, the 4 ideas, that's what postulates are, okay, 4 parts to it, are that elements are composed of small indivisible particles called atoms. 2, atoms of the same element are identical. Atoms of different elements are different. That makes sense, okay? Atoms of different elements combine together in simple proportions to create things called compounds. So we can now, like, cook things with them. And then in a chemical reaction, atoms aren't created, destroyed, or changed, only rearranged. Do those look like common sense to you? Like, could you honestly probably come up with those 2? Looking at the world? I would say so, right? Like, you have a rock in your hand, you throw it across, you put it in fire, whatever, it's still a rock, right? So it's just all these observations, he just took it and made it official, okay? On your page, go ahead and turn the page. And up at the top, I ask you, which of the two? Do I ask two?
Yeah.
Which of the two? And I say 5, and I'm sorry, just focus on the 4. But which of these 2 are actually wrong? So I want you to read through those real quick. They're up on the board, so you don't have to turn your page back and forth. I just want you to think for a tiny bit. Okay, turn to a neighbor and tell them which one you think is actually wrong. Or if you think they're all right, then say that. What did you come up with?
Oh, number 2.
Number 2. All right, so let's focus on number 2 first. Okay? So number 2, atoms of the same element are identical. Atoms of different elements are different. Why? Why are you saying that? Yes.
Because atoms are all made up of the same neutrons and electrons and everything, so they would all look the same or similar.
Okay. I want you to put number 2 down. We're going to come back to it. Okay? We're going to come back to it. Because by the end of the slideshow, you guys should actually know this answer. But put number 2. You don't have to write out the sentence. Just put number 2. Okay? And then I heard a number 4. I don't completely agree with that one. So, because number 4, if it wasn't true, we would be saying that we can create things, right? We can just poof, stuff comes out of thin air, or poof, it disappears, right? That isn't something we really see. So, number 1. Everybody look at number 1. Is that a true statement? Are atoms the smallest, and are they indivisible? So there's no such things as what she was saying over there? Protons, neutrons, and electrons? Oh, right. Yeah, there you go. All right, so number 1 is the other one. So 1 and 2, okay? All right, good. Moving on. We'll come back to conservation of mass tomorrow as well. All right, so Dalton's atomic model is called the billiard ball model. Now, for your test purposes, I would put a star next to the word billiard ball model. You do need to know that. It's the one that looks like just a dot, okay? So Democritus was in charge of coming up with the word atom. Dalton was the one who made it official that it is just a solid sphere and that's it. Okay? So as we go along these, every time you come across a model, I would just put a star next to it. Okay? Okay. All right, so this guy isn't on your notes either. So this guy starts bringing up things called alpha, beta, and gamma particles. All right? So these things allow for someone to do another experiment. Actually, 2 guys to do another experiment. Okay? So his little things where he's accidentally discovering radioactivity allows us to now do these 2 experiments to actually build this model a little bit further. So we can all thank this guy for accidentally doing something. No intention of it, just accidentally. All right. What his accident led to was now J.J. Thomson was able to use a cathode ray tube and come up with the plum pudding model. There's another model. Okay? And I'm going to show you the picture of the cathode ray tube so that then I'll explain what's going on. Okay? So plum pudding model is all about now that billiard ball idea is filled with little negative charges. These little things that are floating around it. Okay? So this right here is your cathode ray tube. Okay? And what's going on is you can see that you have a charge, like a laser beam. You guys kind of see that little green laser beam right here? Yes. Okay? And it's going through. And what these are right here is a charged metal plate. So what he does is he has this straight laser beam going through. And that laser beam is actually a certain type of particle, whether it was going to be a beta or an alpha particle, okay? Those things have their own little charges. So if we put a positive plate next to an alpha, which is a positive-ish kind of charge, do you notice what it did? What does it look like it's doing from the positive plate? Do you guys see what I'm talking about?
No.
What is going here? It is going straight, and then all of a sudden it goes whoop.
Yeah.
Is it repelling or attracting the positive plate? Repelling. Okay. Any ideas why? What do like things do and opposite things do?
Attract.
Okay, opposites attract and like things.
Don't attract.
Everybody together, say the word repel. Let's go. Opposites. Sorry. All right, opposites attract, like things do what? Repel, okay? Get that word into your vocab. So, because he saw that thing repelling that and now being attracted to the negative plate, he's now saying, or that's where he came up with the idea that there are these negative particles, okay? I feel like that should be actually opposite, but we're going to move on.
It's like those
What?
magnets, like with like the little trains or cars or whatever, and like the opposite.
Yes,
is what attracts.
exactly. So she brought up magnets. Yes. You know those certain magnets that you can like flip them and then they like run away from you and
Yeah.
stuff like that? Or they sit there and attract you?
Yeah.
Everybody's played with them at one point in their life. All right. So, cathode ray tube experiment. Make sure you link that up with, who is this? Who are we talking about? J.J. Thomson. Okay. J.J. Thomson is cathode ray tube plum pudding model. So everybody take a look at the picture of the plum pudding model. Okay. I like to call it the chocolate chip cookie model.
Yeah.
Okay. But back then, plum pudding was their chocolate chip cookie. Okay. So we're now in the 1900s. Okay. That means that we believed that billiard ball model for 1,000 years. And then he finally was like, oh, there's actually something inside of those billiard balls. Ha 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 ha. Okay, and he got everybody on board. So now we have plum pudding model. J.J. Thomson. So, and then we have this extra guy. He's not on your timeline either. Okay, but he used his oil drop experiment to basically find the mass and charge of your electrons. So these little parts that J.J. Thomson found inside of the billiard ball, he's now actually giving them a mass and saying that there's actual charge of them. Okay? And this is just a little visual on that. So he noticed the droplets actually taking up space. Okay? All right. Ernest Rutherford. He was the one who did which experiment? Gold foil. Okay, and that's one we talked about on the first day of school. So gold foil experiment. Okay? So he brought in the idea that there is a positive center. Shot a bunch of particles at this gold foil. Okay? They were supposed to go through the gold foil, but they ended up being repelled backwards by something. Those alpha particles kind of have this positive charge to them, okay? So they were being repelled obviously by something that had to be positively charged. We just got done saying the billiard ball is only full of these negative things. So now we have a new idea, okay? And that's, I call it the cream filling model. It's really called the nuclear model, okay? But when you go to look at pictures, it looks like cream filling, in my opinion. So we now have chocolate chip cookie with, I guess I should say chocolate chip muffin. Cupcake? I don't know. Okay. But now we've got that center, okay? So Rutherford is gold foil nuclear model. Looking at your paper, I believe you guys have another positive, or what is it, a light bulb?
Yeah.
Okay, so read that to yourself and go ahead and fill in the answer on that. Okay, so he came up with the Bohr model, and as you can see on the Bohr model, you have different energy levels, okay? This part we're going to see in our first little flame test lab that you guys are going to do. Okay, you're going to see things jumping from energy level to energy level. So his model is going to make sense to you. However, and plus this is what you guys learned in middle school, right? Yeah? Technically, this model only works for hydrogen. Okay, so he had a good idea, but it's oversimplified. And that's kind of why we use it to teach basic chemistry. Okay, because it's easier for us to see it. A lot easier than what Schrodinger brings up. Schrodinger is the guy who does clouds. Okay, and now it does not look like a cloud outside. they're actually going to look like either little figure eights or they're going to look like flowers. Okay? So he came up with our electron cloud model, and we will finish Chadwick tomorrow.